So hi everyone, it's now time to get started for the next session. This session will be chaired by Christopher Berry. Chris, do you want to get things rolling?
Yes, welcome. Hello, everyone. Today we have a invited session, Pulsar Timing Array Discoveries and Gravitational Wave Astrophysics, when we're going to cover the complete spectrum of black holes. We have 3 talks from Sarah Vigeland, Golam, Shaifullah, and Broekgaarden. And starting us off is Professor Sarah Vigeland of University of Wisconsin-Milwaukee. Here is a representative of NANOGrav, who will be talking to us about searching for a gravitational wave background with pulsar timing arrays.
Well, thank you so much. Let me start by thanking the organizers for inviting me to give this talk. It's a real pleasure to be giving this talk on behalf of the NANOGrav collaboration. As I think most of you are aware, we had some pretty exciting results released less than a month ago, and I'm happy to be able to discuss them with all of you here. All right, to start us off, I really love this plot, and actually Christopher Berry started us off by kind of alluding to this. So gravitational wave astronomy really started in 2015 with the first observation of gravitational waves from merging stellar mass black holes. And since then, we've learned a lot about compact objects from the observations made by LIGO. But LIGO is only able to see a small part of the gravitational wave spectrum. Astrophysical sources are emitting gravitational waves over many orders of magnitude. And just as we need different kinds of electromagnetic telescopes to observe the entire universe, if we want to observe the entire gravitational universe, we need different kinds of gravitational wave detectors. Pulsar timing arrays are designed to be sensitive to gravitational waves with frequencies on the order of a few nanohertz to a few hundred nanohertz. Okay, so much lower frequency than what LIGO can see. And it's expected that the main sources in this part of the spectrum are supermassive black hole binaries in distant galaxies. Right. So less than a month ago now, pulsar timing array collaborations around the world had a coordinated release of papers where they presented evidence for a gravitational wave background. I'm going to primarily be discussing the results from the NANOGrav collaboration, of which I'm a member. I would encourage everyone to attend talks at this meeting and read papers from my colleagues in the IPTA, the NPTA, the PPTA, and the CPTA to learn all about their results as well. What I'm showing here are 2 panels from figure 1 of our gravitational wave background paper, showing the reconstructed correlation between different pairs of pulsars as a function of their angular separation. On the left, I'm showing the results of Bayesian analyses, on the right for quantist. You can see that the 2 methods agree well, and that they agree with a theoretical prediction for a gravitational wave background, which is shown as the dashed line. So now that I've told you kind of where we're going, let me take a step back and start at the beginning. Pulsar timing arrays are sensitive to gravitational waves because gravitational waves induce correlated changes in the pulse times of arrival of millisecond pulsars. So pulsar timing array is constructed by making regular observations of many millisecond pulsars, many dozens of millisecond pulsars located all over the sky. And the effect of a gravitational wave will be to induce small changes in when those pulses arrive at the Earth. You need a lot of pulsars to do this because, of course, pulsars are astrophysical objects. They have their own interesting properties. And the pulses have to propagate through the interstellar medium to Earth, which also affects the pulse arrival times. And in order to disentangle a gravitational wave from other astrophysical effects, you need a lot of pulsars because the gravitational wave signal is common among many pulsars, whereas most noise sources are not. Oops, sorry, okay. There are a number of pulsar timing array experiments that are active around the world. shown here in this nice plot by Thankful Cromartie, or nice image, I guess. Right, so as I said, I'm a member of NANOGrav, and I'll primarily be talking about our results. But we also have colleagues in the IPTA, the PPTA, the NPTA, the CPTA, and the MPTA. And all of the pulsar timing arrays collaborate under the umbrella of an organization called the International Pulsar Timing Array, through which we share data and analysis methods and perform analyses on combined data sets that take data from many PTAs and make a single Uber data set. Okay. Golam, who's speaking next, will talk about building a pulsar timing array and the IPTA. I just want to say that the reason we are so excited about the IPTA and about combining our data together is that the sensitivity of a pulsar timing array depends on three factors: the number of pulsars in your array, the observing time span, and the observing cadence. I suppose also the noise properties of the pulsar. But the first three can all be improved by simply adding all of our data together. By adding the data together, we get more pulsars, we get more observations, and we extend that baseline. So when we make these combined data sets, the combined data set is significantly more sensitive to gravitational waves than any of the individual data sets that made it up. So pulsar timing array experiments around the world recently released their separate data sets and gravitational wave analyses that were performed on those data sets. And the next step is to combine our data together and make an IPTA data set, which we expect will be even more sensitive. Okay. And when you observe your pulsars, you're seeing a series of radio pulses coming from the pulsar, and you can time exactly when they arrive. The difference between the observed and predicted time of arrival is known as the timing residual. Okay, this process is called pulsar timing. Okay, the timing model has to include all of the properties that affect the pulsar, things intrinsic to the pulsar, things like the pulsar spin period and period derivative, its proper motion. If it's in a binary, that will also affect the pulse times of arrival. So you have to take into account all of those things. And by doing so, it allows you to make extremely precise measurements of the properties of the pulsars. Okay, shown on the left are pulsar timing residuals for one of our pulsars, J1909 minus 3744. The colors indicate which receiver backend took the data. Okay, this pulsar is one of our best timed ones. This is just to give you an idea of how precisely you can time these pulsars over long periods. This one has been observed for more than 15 years. Now, when you're thinking about the residuals, you can think of them as having different contributions from different effects. One comes from marginalizing over the timing model. One comes from the effect of white noise, which includes radiometer noise. And the final one is red noise. Red noise is an astronomy term, which means noise where there's more power at low frequencies than high frequencies. And there are many possible sources of red noise. Some are intrinsic to the pulsar, like spin noise. Some are related to the pulse's propagation through the interstellar medium. And the gravitational wave background is a form of red noise. It has more power at low frequencies than high frequencies. You're going to hear me use the term red noise a lot. So I thought I would just take a little bit of time to explain exactly how we model it. So we model it using these two terms, F and C. So F is a matrix, okay, that we use to set up the Fourier basis that we use to describe red noise. Okay, and so you're going to have a series of frequencies. Okay, we start with the lowest frequency to which we're sensitive, which is 1 over the total span of our observations. For the NANOGrav 15-year data set, this is about 2 nanohertz. Then we just go up in integers. So we have 2 nanohertz, 4 nanohertz, 6 nanohertz, etc. Okay, at some point, you're going to truncate that sum. You're not going to actually have an infinite sum, which is fine because by definition, red noise has more power at low frequencies than high frequencies. So if you move to high enough frequencies, the strength of your red noise is going to be very low. Okay. The C's are a vector of coefficients for each of your Fourier modes. So you can measure how much signal you have, how much power you have, depending on what units you're using. You have how much red noise you have at each of these frequencies. Okay. You could also assume some kind of underlying power spectrum. We often assume a power law power spectrum. Okay. All right. So the way that I like to think about a pulsar timing array signal model is that you have all of your pulsars, hopefully more than 3. Each one is going to have its own timing model, its own white noise, and its own red noise. So these are unique to each individual pulsar. And then you have the common signals, which affect all of the pulsars. So there are common sources of noise. For example, if there's some kind of drift in the time standard, that would, of course, affect our ability to time all pulsars. Then finally, there's the gravitational wave signal, which is common to all of the pulsars. This helps us differentiate between a gravitational wave and noise unique to the pulsars. The other way that we can distinguish between gravitational waves and other types of signals is by looking for the type of correlation. Okay, so for a gravitational wave background, you're going to get a correlated change in the pulse times of arrival, and the correlation is going to depend on the angular separation between your pulsar pairs. So here is our little cartoon pulsar, and this one does have just 3 pulsars. We're going to call them star, circle, and cross. So that gives you 3 pulsar pairs, right? You have star, circle, circle, cross, star, cross. For each pair, you can measure the angular separation between them. And on average, you would expect that the correlation coefficient for each pair should follow this curve on the bottom left, which we call the Hellings and Downs curve. So you can see that it is maximum if the two have a very small angular separation. Then as you move them further apart, it goes to 0, then they become anti-correlated, then it comes back up to 0, and then it goes up again, but not as high as it is at 0 degrees. Now, one thing to note about this curve is that all of the correlation coefficients are less than 1. And in fact, for many ranges of angular separations, they're really quite small. Okay. If we look at kind of an n pulsar by n pulsar matrix, okay, you can construct this matrix. On the diagonal, you have the pulsar correlated with itself, so that's 1. Okay. On all the off diagonal elements, you have the correlation coefficient for each pair. You can see that those values tend to be small. They're certainly smaller than the diagonal elements. But as you increase the number of pulsars, of course, the number of off diagonal elements is going to grow faster than the number of diagonal elements. The diagonal elements will grow like the number of pulsars, number of pairs grows like n squared. So as your pulsar timing array gets bigger, the effect of the correlations becomes more significant, and it grows faster than the pulsar, the pulsars correlated with themselves. Okay, now measuring this kind of correlation signature that you in the data is very important because it's a way that we can do tests of gravity. In general relativity, there are only 2 gravitational wave polarizations, the plus and the cross. But the most general metric theories of gravity can admit up to 6 polarizations. The other 4 polarizations would induce correlations, but different than what we see from the plus and the cross. So you would get a correlation pattern that's different from the Hellings and Downs curve. So this is a way that pulsar timing arrays can put constraints on theories of gravity, on alternative theories of gravity, or possibly find evidence for alternative theories of gravity by looking at the correlation pattern and seeing whether it is indeed Hellings and Downs or whether there is a sign of a pattern induced by one of these other modes. Okay. But gravitational waves aren't the only sources of a correlated signature in our data. Okay, some noise sources can induce correlated signals. Some noise sources also induce common red noise, but they don't induce any kind of correlations. The correlation on average is 0. However, there's no known noise source that induces correlations that look like Hellings and Downs. So that is unique to gravitational waves. A clock error, which I mentioned earlier, would induce monopole correlations because it would affect all of the pulsars in the same way. Okay, so that would be like a horizontal line. You can see that in the third panel from the top, third row from the top on the in the figure on the right. Another type of correlated noise source is an error in the position of the solar system barycenter. So when we do pulsar timing, you don't want to just reference the pulse times of arrival to the telescope, because the telescopes are not inertial reference frames, and there are also different telescopes used. So instead, everything is referenced to the solar system barycenter, which we can take to be an inertial reference frame. But that means you have to be able to correct for the propagation time between your observatory and the barycenter. So you need to know the position of the barycenter very accurately. And a few years ago, this was an issue for pulsar timing arrays. And the expected correlation signature of such an error is a dipole. Okay, so now that I've talked about how pulsar timing arrays detect gravitational waves, let me talk a little bit about the sources. I am going to focus on black holes, but there are cosmological sources that may be producing nanohertz gravitational waves, such as phase transitions in the early universe and cosmic strings. I am not an expert in these cosmological sources of gravitational waves, but I encourage you to attend Andrea Mitridati's talk. In this meeting, he will be talking about that in more detail. There are also other talks about cosmological sources during this meeting, which I'll highlight at the end of my talk. Okay, but we expect that, well, we know that galaxies, massive galaxies, contain supermassive black holes at their centers. We also know that galaxies merge. When massive galaxies merge, the two black holes will come together and form a binary. When they reach subparsec separations, they will be emitting gravitational waves in the pulsar timing array band. So if you look at this figure here, that's the second panel from the left. Okay. When they're in this at the separations, the orbit is evolving, but it is evolving slowly compared to a human lifespan. And so gravitational waves from a single one of these sources are often called continuous waves, because if it's circular, it's going to be emitting just a single gravitational wave frequency, like a single note. Okay. Now, eventually the black holes will get closer together and they will merge and form one even more massive supermassive black hole. Pulsar timing arrays are not sensitive to the oscillatory part of the merger. However, they are sensitive to the gravitational wave memory effect, which is left over after the merger. So if you look very closely, you will see that the yellow line before and after merger, the mean is not in the same place. There is a vertical offset. That vertical offset is the gravitational wave memory effect. Now, in addition to individual sources, pulsar timing arrays are sensitive to the gravitational wave background, which is made up of gravitational waves emitted from all of the supermassive binary black holes in the universe. And for a while now, theorists have predicted that the gravitational wave background is actually the dominant source at these frequencies. Individual sources lie below. Okay, so first you detect the gravitational wave background, which is kind of a hum of all the gravitational waves. And then after you detect that, you're able to pick out some of the loudest sources and individually resolve those. The gravitational wave background tells you about the overall population of supermassive black hole binaries. Roughly speaking, the amplitude tells you about things like the mass distribution of supermassive black holes and the merger rate and time scale, since binaries form in galaxy mergers. The shape of the spectrum is determined by the astrophysical effects driving the black holes to merge. If you assume that the background is comprised of gravitational waves coming from circular black holes black holes in circular orbits that are evolving only due to gravitational wave emission, then you can derive analytically that the power spectrum should follow a power law, and it should go like frequency to the minus 13/3. But if either one of those assumptions is not true, then you're going to get a change in the shape of the spectrum. So if some fraction of them have significant eccentricity, for example, the shape of the spectrum will be different. If environmental effects are driving the merger during part of the time they're emitting in the nanohertz frequency range, then that will also change the shape of the spectrum. And in particular, it induces a turnover. Okay, so at very low frequencies, the shape of the slope of the spectrum would be different, and then it would turn over when it reaches the region where the emission is being dominated, the orbital evolution is dominated by gravitational wave emission. Okay, so there's a lot about the population of supermassive black holes and their environments that we can learn from observing the gravitational wave background. So now let me talk about the NANOGrav 15-year data set and the gravitational wave results from analyzing that data set. The 15-year data set consists of 68 pulsars observed for up to 15.9 years, 67 of which were used in the gravitational wave searches. One pulsar has not been observed quite long enough to make contributions to the gravitational wave searches, but it certainly will have been observed long enough by the next data set. Observations were made with the Arecibo Observatory and the Green Bank Telescope, and for the first time, the data set contains data taken with the Very Large Array. Joe Swigum will be giving a talk on Tuesday about the data set. On the left, shown just some visual representations of the pulsars. On the top, the sky positions of the pulsars, which with the telescope or telescopes that observe them indicated by the marker. Most pulsars are observed with either Arecibo or Green Bank, but some pulsars are observed with multiple telescopes, only a few though. Okay. On the bottom, I'm showing the distribution of angular separations probed by our pulsar pairs. This is very important for being able to detect correlations and also distinguish the type of correlations. You want to have good coverage over a range of angular separations. The Hellings and Downs curve goes, plus, minus, plus. So you need to have pulsar pairs across that whole range so that you can actually see it, do that. All right, so for the first time in the NANOGrav 15-year data set, we find evidence for Hellings and Downs correlations. We find evidence in both our Bayesian and frequentist analyses. So starting with the Bayesian analyses, we find a preference for a common red process with Hellings and Downs correlations over one with no correlations. Okay, so if we look at this flow chart of Bayes factors at the bottom, we find that a model with common spectrum red noise is preferred over one with intrinsic pulsar noise only by a factor of 10 to the 12. A model with Hellings and Downs correlated common spectrum red noise is preferred over one without correlations, but with common spectrum red noise by a factor of over 226. Okay. Now, when we model this common spectrum red noise, we're modeling it, as I said before, and we're modeling it over a frequency range from 2 to 28 nanohertz. The figure on the top right is the one I showed before. It is a reconstruction of the correlation coefficients. Here, this is using a spline model with 8 spline points. The 8 points have been chosen to capture features of the Hellings and Downs curve. So there are 2 points at the ends, 1 at the theoretical minimum, 2 points at the zero crossings, and then 2 additional points just to add more flexibility to the fit. Then the dashed line shows the Helens and Downs curve itself so that you can see the consistency between them. For the frequentist analyses, we use something called the optimal statistic, which is a maximum likelihood estimator. We use it in two ways. One is as a detection statistic, so basically measuring how significant it is to measure correlations consistent with Helens and Downs versus there being no correlations at all. And the second way is as a binned estimator. Now, when we use it as a binned estimator, which is what we are showing on the plot, in the plot on the left, we include pair covariance. So each pulsar will contribute to multiple pairs, right? So the points on this plot are not independent of one another, just as a warning. Okay. Now here we're using 15 points for this binned estimator, and you can see the Helens and Downs curve is again the dashed line. You can see that they agree well. I will say that the choice of the number of bins will make it visually look different, but you will find equally good fits for a range of binnings. Okay, now in order to determine the significance of these correlations, we have to compute the background distribution and of our detection statistics, either the Bayes factor or the optimal statistic signal to noise ratio. And then we compare our measured values to those background distributions. The way we do this is something called phase shift. So with a phase shift, what you do is you take your Fourier basis, right, with all of your frequency components, and you just add random phases to them, random phase offset. Okay, and you do this per frequency and per pulsar. And what this does on average is it breaks the correlations between different pulsars. Okay, so we did this for the Bayesian analyses and for the frequentist analyses. We got these background distributions and we compared our measured values. For the Bayesian analysis, we find a false alarm probability of 10 to the minus 3, which is a 3 sigma Gaussian equivalent significance. For the optimal statistic, we find a false alarm probability of between 10 to the minus 5 and 10 to the minus 4, okay, which is a 4 sigma Gaussian equivalent significance. For the optimal statistic, we also computed the background estimation two other ways. One, using simulations where we simulate data sets with only common uncorrelated red noise and no correlations present. The other way was we actually analytically calculated the background distribution, which follows a generalized chi-squared distribution. All of these methods agree well, and from that we conclude that the significance of the correlations is between 3 and 4 sigma, depending on the analysis method and the method of background estimation. Now let me talk about spectral characterization. Okay, so this plot on the left has a lot going on. So let me explain it, explain each of the pieces. Okay, so the gray violins are showing the spectrum of a Helens and Downs correlated red noise process. And it's modeled over 14 frequency bins, so from 2 nanohertz down to 28 nanohertz. Okay, so each one of these violins is the posterior on the amplitude, those amplitude coefficients that I showed earlier when I had my little equation, the posteriors that you get on those from a Bayesian analysis. Okay, and there's no assumption that there's any kind of relationship between those amplitude coefficients. Okay. We can also fit the power spectrum, assuming some kind of model, and it makes sense to fit a power law model. One, it's sort of, a standard tool in astrophysics, but also we do expect the background to look like a power law if it is being produced by circular supermassive binary black holes evolving due to gravitational wave emission. So that's what's shown in the blue. We show the posterior on this power law fit. Okay, and you can compare that to the gray violins and see how well they fit, how well they agree. Okay, now one thing to note is that if we fix that spectral index, that gamma, to the 13/3 that we predict for circular black holes evolving due to gravitational wave emission, You can also get a power spectrum out, but it is steeper than the best fit when we allow that spectral index to vary, okay? Before I move on, I want to just add that here this plot is truncated, so it only shows the lowest frequency bins. We did explore higher frequencies as well, and we found that the spectrum transitions to flat at about 28 nanohertz. That's why we focused our results using only frequencies from 2 to 28 nanohertz. Above that, the spectrum is white noise dominated. All right, so if we use this power law power spectrum model, we find a preference for a spectral index gamma that's shallower than 13/3, okay? So that's shown in the corner plot on the bottom left. However, the recovered posterior on the amplitude and spectral index are sensitive to noise modeling choices. In particular, we need to model changes in the dispersion measure, which is produced by dispersion of the pulses by the interstellar medium along the line of sight. There's sort of two ways that we do this in the pulsar timing array world, and different choices lead to posteriors on the power spectrum that are broadly consistent. But if you model the dispersion measure variations as a Gaussian process, you do recover a spectral index that is more consistent with 13/3. Finally, let me talk about some of the checks that we did of our data set. Okay, one important property of the gravitational wave background is that it should appear in many pulsars, not just be limited to a small handful. One way that we quantify this is through a dropout analysis, where we turn the gravitational wave signal on and off in individual pulsars. So you're essentially doing model selection between two models, one where you have a gravitational wave background in all n pulsars, and one where you have a gravitational wave background in n-1 pulsars. Okay, and then you see which one is preferred, and you do this for each pulsar. Okay, the base factor between these two models is called the dropout factor, and it's shown here in the plot on the left. Okay, each dot represents a different pulsar, and they're broken down in terms of their total observing span. So for the very short timed pulsars, the dropout factors are very close to 1, which is not surprising. If they're short timed, the lowest frequency that they can probe is pretty high, and at that frequency, the gravitational wave background is not very strong. So it's not surprising that they are not really able to tell whether it's there or not. But for the longer timed pulsars, we do see a range in dropout factors, and that most of the dropout factors are high, okay, indicating that they show that that pulsar in particular shows evidence of this signal. Another cross-validation tool is to look at to compare results taken with different telescopes. So what we did was we split the data into two data sets, one containing only observations made with Arecibo and one containing only observations made with Green Bank. For most pulsars, they're observed with either one or the other, so this is trivial. But for some pulsars that are observed with both, this required making two independent timing solutions, one only using the data taken by Arecibo and one only taking the using the data taken with Green Bank. Okay, data from the very large array was just completely excised. Observations with the VLA started relatively recently, and there just aren't enough observations or enough pulsars to really have a data set that would give interesting constraints on its own. Okay, now both the Arecibo and Green Bank data sets show evidence of a common process, and the power spectrum, amplitude, and spectral indices are shown, posteriors are shown in the corner plot here. You can see they're broadly consistent with each other and with the posteriors from the full data set. The Arecibo only and Green Bank only data sets also show evidence of Hellings and Downs correlations, but at a reduced significance compared to the full data set. So the full data set gives an optimal statistic SNR of 5, For Arecibo only, it's 2.9, and for GBT, it's 3.3. Okay, this seems consistent with our expectations of how of what we should be able to get with only observations made with one telescope or the other. About half of our pulsars are in the Arecibo only dataset and half are in the GBT only dataset. So that's the reason for the reduction in sensitivity of the correlations. Now, the next thing I want to talk about is evidence for an additional correlated process. There is some evidence that there may be a monopole correlated signal present in addition to a Hellings and Downs correlated signal. Okay, most of this evidence comes from the multiple component optimal statistic analysis, where we find a preference for a model that contains Hellings and Downs plus a monopole versus Hellings and Downs only. Okay, the Bayesian analyses also show some evidence, although it's not as strong. But if there is evidence in the Bayesian analyses for a monopolar correlated process, it is constrained to a single frequency. It's not present over the entire range of frequencies that the Hellings and Downs correlated process is present. It seems to be confined to 4 nanohertz, okay? But the base factors are between 1 and 10. So there's not strong evidence for this process, for this signal being present. It is very interesting, and it's certainly something that we will continue to look into in future data sets. All right. Okay, I'm only going to touch briefly on implications for supermassive binary black holes. I encourage you to read the paper that we wrote about it. The observed power spectrum is consistent with a gravitational wave background produced by supermassive binary black holes. There is some preference for models where the black holes interact with their environments versus models that only include gravitational wave emission in their evolution. However, the range of theoretical parameter values from both types of models are very broad. And our constraints on the amplitude and spectral index are also broad at this point. Okay. The amplitude is high, but it is within the range of expectations, and it implies some combination of relatively high black hole masses, high rates of galaxy mergers, and efficient binary in spiral. Now, the results that I've just talked about are only some of the results that came out on June 29th, UTC. Through the IPTA, we coordinated the release of 18 papers from NANOGrav, the IPTA, the NPTA, the PPTA, and the CPTA. And they were all posted on the archive in this order. So you can go look them up. The archive numbers range from 213 to 16230. A number of people will be discussing these results at the Amaldi meeting, and I strongly encourage you to attend those talks and hear more about these results from them. These results don't just include the results of gravitational wave background searches, they also include searches for different types of gravitational wave signals and interpretation of those results in terms of supermassive binary black holes and also cosmological sources. So there's a wide range of science that we've done with these data sets. Okay, the IPTA is preparing a paper comparing the gravitational wave background results from the combined IPTA and NPTA data set, the NANOGrav data set, and the PPTA data set. So these are some preliminary results that show that the power spectrum for the gravitational wave background are broadly consistent across the different data sets. And for more details, please see Paul Baker's talk in the next session. All right, so in conclusion, pulsar timing array collaborations have recently published evidence for a gravitational wave background at nanohertz frequencies. The NANOGrav 15-year data set shows evidence of Hellings and Downs correlations with false alarm probabilities between 10 to the -3 and 10 to the -4, which is 3 to 4 sigma Gaussian equivalent significance. Other pulsar timing array collaborations have also published analyses of their data sets. And the next steps are to publish a paper comparing the results across PTAs, and then to combine all the data and analyze an IPTA data set. The signal that we are seeing is consistent with an astrophysical population of supermassive binary black holes, but exotic sources cannot be ruled out. Now, this is a very exciting time for pulsar timing arrays. I really think this is just the beginning of a lot more exciting science to come. And I will take questions now. I just want to leave it at this slide, which lists sessions that have other pulsar timing array talks so that you can learn more about our science. Thank you.
Thank you, sir. That's perfect timing. We have the Q&A feature on Zoom for people to ask questions. So I'd like to ask people to chat those in there. While I give people a moment, I would like to use the my position as chair to ask, on the comparison plot you have of the different PTA results. Yeah, I know this is something from Paul's talk. I noticed that the CPTA results are not shown here. Is that because the data aren't available, or their analysis is different in some way, so you can't do a direct comparison?
Right. So that's some of that is a little bit of politics. The EPTA, NPTA, NANOGrav, and the PPTA are all full members of the IPTA, and the CPTA has observer status. The 4 PTAs that I've already listed, they've all pulled their data together and have been working on this project for a while. The CPTA, we don't have access to the CPTA data right now, as far as I know. Their analysis is also quite different from ours. I'm very interested in learning more about how they do their analysis and doing some kind of comparison between their results and ours.
Okay, so we have a few Q&As entered now. So we could start with David Keitel's question. Huge congratulations. He was wondering, are the Arecibo only pulsars lost for the near futures, or if other telescopes can pick those up?
That's a great question. Let me go back to this slide. Okay, let's see. So if you zoom in, right, one of the things you might notice is that the Arecibo pulsars are all within a narrow declination range, whereas the GBT pulsars are a much larger declination range. So Green Bank can see everything Arecibo could see, but the reverse was not true. So GBT has picked up the Arecibo pulsars, fortunately. Now, it did require rejiggering our observing schedule because, of course, we had a certain number of hours we used at Green Bank. Now we're trying to observe more pulsars. So that was complicated. We also have started incorporating data from another telescope, CHIME, in Canada. So that will be in the next data set. Joe Swigum can give you a lot more details on that, but the short answer is that we haven't lost pulsars, but it did require rejiggering the observing schedule to be able to cover things with now Green Bank, the Very Large Array, and CHIME.
Cool, thank you very much. We have another question. We also have we have another question from Evan Keane. He says the significance is 3 sigma Bayesian, but you also mentioned it being 3 sigma in Arecibo and GBT separately and 5 sigma combined. He thinks he misunderstood the distinction between these and asks if you could explain a little bit more.
Right, that's a very good question. So the null distribution of the optimal statistic, which is what it's the frequentist method we use to get these signal to noise ratios. The null distribution for that is not a Gaussian. And so you can measure an SNR by taking the amplitude and then dividing it by the uncertainty, but it doesn't map to a p-value or a significance level in the way that we expect. So an SNR of 3 does not mean 3 sigma Gaussian equivalent. That's why we had to do these phase shifts and sky scrambles. If you look very closely, you can see, right? at 4 sigma Gaussian equivalent, you're actually at an SNR of between 5 and 6, right? The significance levels here are computed in the following way. We compute the p-value, and then we relate that to the sigma level for a Gaussian with the same p-value. Yeah.
Great, thank you. We have an anonymous question, and I think I should also encourage any early career people, even if you're shy asking a question, please do be encouraged to do so. Here's an anonymous question. Thanks for the great talk. What are the ideas on what causes the 3.95 nanohertz monochromatic monopole?
Well, I mean, I could give you a long list of things that we've tried, but we've tried many things. Okay, we've tried just a simple sinusoid model. We've tried a continuous wave signal. So imagining you have a gravitational wave coming from just a single binary that's emitting at that frequency. Right now, the significance of the signal is low. And so you can't really tell, you can't tell the difference between these different models, right? Just a pure sinusoid fits the data. A continuous wave, it's not a bad fit, but it doesn't really improve things that much. So right now we just don't know. But yes, one of the one possibility that has come up a lot is that it could be gravitational waves from an individual supermassive binary black hole. But if that is what it is not at a detectable level yet. It's definitely something we're interested in looking into in future data sets, and very much interested in looking into whether it's present in the IPTA combined data set.
Thank you. Okay, we've got a question here from Musin Al-Jaf. Thanks for the amazing talk and congratulations. They were wondering what are the effects of Earth's movement within the solar system and our galaxy and pulsar timing, and what effects filtered out from the pulsar timing rate. So I guess this refers to the ephemeris issues that you referred to earlier.
Right. So I'll answer the one about movement through the galaxy first. Okay, that one is not a very large effect, although it is possible to put constraints on galactic acceleration from binary pulsars. Right now it's just constraints, and it's not significant enough that we include it in the gravitational wave analysis. As for movement within the solar system, yes, that is definitely very important. That is where we have to really worry about the ephemeris use. Many years ago, this was an issue because of basically uncertainty in the orbital position of Jupiter was showing up in our gravitational wave searches. Fortunately, that's not as much of an issue anymore because the Juno mission provided much better measurements of Jupiter's position. And so the ephemerides that have been made since the inclusion of Juno data are much more precise.
Okay, we have a question here from Hippolyte Leclerc. Congratulations on the talk. They were wondering how the evidence for the Hellings and Downs curve changes with the number of Fourier bins you consider, and whether the evidence reduces if you consider the 4 first constrained Fourier bins.
Right. So the evidence does change as you change the number of Fourier bins. If you have very few Fourier bins, you just don't have a lot of signal, and so the evidence is smaller. It grows as you increase the number of bins, and then it actually starts to dip down again. We chose to use the same number of Fourier bins for the Hellings and Downs base factor calculations as we use in all of the other analyses. So that's 14, from 2 to 28 nanohertz. Okay, it's not surprising that as you move to higher frequencies, you're getting, you're still able to measure the common spectrum red noise process, but you don't have significant correlations because the correlation coefficients are small. But we chose not to tune our analysis to get the highest phase factor. We use the same number of frequency bins for the whole thing, but this is discussed a bit in the paper.
Cool. Thank you. So we have a couple of questions left. Let maybe see if we can answer these very quickly. We do have a few minutes break before the next talk. Jan Novak's asking whether it's unexpected that we observed a gravitational wave background or not. I guess this might depend on the type of background we are considering.
It has long been expected that the first signal that pulsar timing arrays would see would be a gravitational wave background. And so for a long time, that has been our priority, developing methods for that kind of search.
Cool. Okay, and anonymous question to end on. You mentioned the memory effect in gravitational wave data. Does it only affect these interferometer data, or does it vary for the different pulsars?
Yes, right. So memory effect is very interesting. Essentially what it does is when the memory, any gravitational wave signal affects both the Earth and the pulsars. And then all the pulsars, right, are at different sky locations and at different distances, so different points in the galaxy. If the memory effect is affecting the Earth, it affects all the pulsars. And what it does is it makes it look like all of the pulsars changed their spin rate, like at the same time. They all just started spinning at either a faster rate or a slower rate. If it only affects one of the pulsars individual terms, you'd still see it, but it would be very difficult to tell, if not impossible actually, to tell that that's a gravitational wave and not something intrinsic to the pulsar, because pulsars do change their spin rate occasionally. Millisecond pulsars don't tend to do it as much as regular pulsars, but at least one has been known to do this. It's called a glitch. So for burst with memory searches, you really have to look for something that's happening in all of the pulsars at the same time.
Thank you very much, Sarah. I hope everyone will join me in thanking you for an excellent talk and some exciting results.
Thank you.
We now have a few minutes break until the second talk of this session, where Golam will tell us about building a pulsar timing array and the International Pulsar Timing Array. That talk will begin on the hour, so potentially time for everyone to go and grab themselves a coffee. Thank you.
My name is Golam. I'm a postdoc at the University of Milano-Bicocca, and I work extensively on pulsar timing arrays, especially as a data analyst. So moving on, I mean, if you want to talk about pulsar timing arrays, you have to talk about pulsars, and if I want to talk about pulsars, I have to at least drop a brief mention of one of my personal heroes, Dr. Justin Bell-Burnell, who happened to be this incredible graduate student who was spending a lot of time looking at mostly scratches on paper and happened to make one of the most fantastic discoveries possibly of the century. Pulsars basically are these giant compact remnants. Well, giant compact sounds contradictory, but it's a compact object which is left behind after a supernova explosion from a star which is between 8 to 20 solar masses, which at the end produces a very dark, in the sense of the optical light emission object, which also can be very intense magnetic field. These objects, as they collapse to form their compact cores, they also happen to pick up a very rapid rotation, and because this is now like a magnet spinning around in space with a very thin plasma hanging around, it is able to set up these giant electric currents, which sets up a bunch of processes, leading eventually to some kind of emission along magnetic poles. If it's fortunately aligned or misaligned with the spin axis, if the magnetic pole is misaligned with the spin axis, this beam will then sweep over a distant detector, distant human being sitting on Earth. Most likely you will not pick it up because it's mostly in the radio regime. But if you are lucky enough to have a convenient radio telescope at your disposal, then you would see this beautiful pulse emission from these objects. And if these are like little blips, little ticks, you can also try to measure some sort of time standard by them, or you can take your clock and say, this pulse arrived at X moment, and call that a time of arrival for the photons making up that pulse. As I said, I'm going to be a little bit historical in some sense, and give a little background of why we need to do some things which are not really PTA science before we get to PTA science. Of course, the first thing you need to build a PTA is to find a bunch of good pulsars in the sky. On this slide, I've just plotted out the very first discovery. Justin Bell standing in front of the giant interplanetary scintillation array at the Muller Observatory. High-speed telescope. In fact, the thing that distinguished the IPS array from other instruments around it was the fact that it had two modes. One was a normal speed mode where the charge roller rolled over at a rate of a unit distance per second, and then there was a little switch that made it go faster in the millisecond, and that little invention is what basically enabled the detection of first pulsar and then set up a whole bunch of other discoveries. So what you see here is basically what Jocelyn's task was to look at these pen chart recordings of voltage fluctuations produced by radio emission mapped to different longitudes on the sky. And she noticed that there was this little bit of stuff, as she called it, which would repeat every so often, well, which would repeat every single day. And it had this weird property that it would fluctuate. The intensity of this object would fluctuate with a value between 0 and 100, and it was visible almost every day, but occasionally it would also disappear. And then when you switch to the high-speed mode of the same pen chart recorder, you could zoom in and see that 100% scintillation, as it's called, that Jocelyn was observing, would then appear as a series of pulses or ticks, which gives the whole root for the name of these class of objects, which is the pulses of pulsars. We don't do this anymore. Thanks a lot, Scott, and a bunch of other people. So a quick disclaimer, there are a few names and few papers credited on my slides, but please do keep in mind that there's a huge body of work behind this. It's a little hard to list every single person who's ever worked on these things. But if you need references, please feel free to reach out either during question time or after. So the way we do pulsar searching now is we record the electrical signals in what is called the Stokes mode, and then convert it into the Fourier domain through the discrete Fourier fast Fourier transform, and then search pretty much the same way as this little periodogram up here. What we're looking for is a periodic signal that sticks out and which we haven't previously associated with a pulsar-like object in the same part of the sky. What is plotted below, are the results from a very, very common use program, Presto, developed mainly by Scott and a bunch of other collaborators, which uses the FFT-based search, but adds on a whole number of other features which allow you to search for binaries which might be accelerated, the Accel search method, extreme acceleration cases where the pulsar is jerked around in its system, and there could be some other phase modulations present, which would also require a modification to the simple period of such, which doesn't work when you want to look at systems very extended binaries or in interacting or eclipsing binaries, for instance. There also exist non-Fourier methods of searching for pulsars. These also work with some degree of success, but between Fourier and non-Fourier methods, the Fourier one dominate in terms of the number of anonymous attendee. Can you hear me now? Okay, I'm just going to move the phone a little bit closer to myself. Yeah, so once you've found the pulsar, the next step, of course, is to build a model for it. Now, if it's a simple pulsar hanging out by itself, all you need to really model is its rotational properties. Well, that's not completely true. There are more details that we'll come upon a bit later, because even though we might pretend to ourselves that an isolated pulsar, we call them, is just like this magnetic monopole hanging around in space, being spun around by a magnetic field which is rotating, leading to the production of a large voltage. It's not quite that simple, because on every rotation, because the emission itself is linked to a bunch of physical processes, not all of which are well understood or well identified, or static in time. What you would see is that within every single rotation, the pulse, which looks so uniform here in the middle panel, it doesn't quite look exactly the same for every single rotation. What makes it a bit more complicated is you could have a pulsar, which is hanging around at the center of this blue orb, and around it there is a companion. Now this will introduce a whole other set of accelerations, mostly Doppler shifting the frequency in a specific way. You would then need to model the properties of the binary, including the separation, the binary period, and other things such as the location of, well, some sense of the 3D geometry as in projection on the plane of the sky. These models exist, and when we have enough data, it becomes a very interesting thing to do pulsar timing, because we can make very, very precise estimates of all of these parameters. And that leads to the term high precision pulsar timing, because if you observe a pulsar if you observe a pulsar long enough, the very first thing you notice is that you have incredibly high precision on the rotational properties. And we can predict, we can have an observation taken 40 years in the past, and we can build a timing model using data from that year. And if things work out, which sometimes, not often, you could continue that model up to the present, and you would be able to predict with a fairly high degree of accuracy the time at which you would see in the millionth pulse, the 20 millionth pulse. And this has been done a few times for a few special pulsars, which we know are pretty stable. But pulsars are also unique and cranky sometimes. So it doesn't always work. But that leads to a lot of exciting physics, because the things that don't work for simple pulsar timing are where all of the exciting physics lies for a lot of pulsar astronomers. However, the one good thing about being able to find some stable pulsars and find them for a very, very long period of time is that you can then construct a very nice model, a very deterministic model, which you can subtract off from the data you observe and obtain a set of timing principles. as I mentioned, the timing model of the pulsar contains basically astrometric properties, where is it located, how fast is it moving in the sky, pulsar rotational properties, how rapidly is it rotating, does it rotate without undergoing glitching, which Sarah just mentioned. Is it hanging around in a binary? Is it hanging around with tertiary? These are fairly deterministic in their measurements, and once we have observed the pulsar for a relatively long period of time, say a few years, we can make very, very precise measurements up to 1 part in a million precise for each of the parameters. So what is often more difficult is modeling the dispersive delays that the radio waves and the pulsar suffer as they travel through the ionized stellar medium down to Earth. Any low frequency processes, and you see that I played that Super Bowl because that's where most of us are interested in. That's what most of us are interested in. Well, at least one kind of that. And there's also this annoying thing about pulsars that the pulses are regular, but not really. So they can be a little different. Each pulse or each group of pulses can be ever so slightly different from the other, causing a slight variation between observation pulses at the time, producing what is called pulsar jitter. Very quick primer. I promise these are the only 2 equations I put up. You don't even have to worry about the equation on the left. Just look at the picture on the right. All we are trying to do in pulsar timing is to measure the time of arrival of a group of photons making up a pulse, and then translate it back to an inertial reference frame, which is what the equation below basically is telling us. That if we want to translate an observation, the time of arrival at a telescope to the solar system barycenter, we need to correct for the time measured. Sorry, there are a few typos. We need to translate our reference system first to the center of the Earth and then back to the solar system barycenter, accounting for gravitational effects set up by the solar system. And in case the pulsar is hanging around with a binary, then we need to account for gravitational delays by the time. I heard someone chiming in. I hope I'm still audible.
I think so. Just keep the phone close.
All right. What we are trying to do is to count the pulses in some sense. And the way you would count the pulses is by observing one pulse, and then if you have a good idea of the spin frequency and the rate at which that spin frequency is changing, then you can easily construct a pulsar timing model by counting every single pulse that you see. And that's what I showed in the slides previously. Why do we want to use this special class of pulsars for millisecond pulsars? I didn't quite explain that we do want to use those. But if you want to make very, very precise measurements of fluctuations in time, then of course you want the best instrument to measure time with. So one good thing about millisecond pulsars, faster spinning pulsars, is that their pulses become very, very similar and have a very high signal to noise ratio as you start adding together a number of them. And this is actually true for any pulsar, but of course, if you observe a slowly spinning pulsar for 20 minutes, and if you observe for the same 20 minutes a pulsar which is spinning at 100 times as fast as a slowly spinning pulsar, then the total number of pulses you're adding together becomes a factor of 100. And therefore, in 20 minutes, you will have observed 1 million pulses, the average of which is going to be incredibly stable. And that's over here on the right-hand side of the slide. where the pulses do look slightly different, but when I extract a time of arrival by comparing it against the standard template, the difference I get is really small, and that's less than actually the error bars on this are 200 microseconds. 200 nanoseconds. So that's an incredibly precise measurement to be able to make over a long duration of time. How long? Millisecond pulsars are incredibly stable clocks. When you get to the regime of a few years to tens of years and even further, at which point they are as precise as atomic clocks, which is why you will often hear this said about IPTA work, that we use pulsars that are as precise as atomic clocks. But of course, we have to keep in mind that precision is limited to a window of time. Okay, so I hope you are convinced that QA is becoming incredibly stable as you average more and more pulses. So I wanted millisecond pulsars to produce my pulsar timing array. And also from Sarah's talk and by and some of the things that I will discuss a little bit further on. I want to avoid individual noise in pulsars to try to measure the effect of gravitational waves or any other possibility in between me and the pulsar. So the best way to do that is to use an array of millisecond pulsars. Why do we care about PTAs? Because simply put, it's one of the few, it is the only experiment that is going to open up the window of nanohertz regime gravitational waves for us, which is an excellent place to search for supermassive binary black holes and stochastic backgrounds from a whole bunch of sources. A lot of those are listed in Sarah's talk. Particularly if you're into cosmology, this is where your stochastic background lies. This is what you're mainly interested in. Okay, so a little bit about the hard part of building PTAs. So you found your pulsar, you are observing it, you know how to deal with a bunch of different things that are happening to the radio wave propagation through the ionized interstellar medium and other ionized components. And then your observations, the radio waves arrive at Earth, you have this giant fancy radio telescope, which you collect all of them into a receiver. But unfortunately, somebody, maybe your bestie, is hanging out with their mobile phone, and that sends off a bunch of radio signals, because we all share the same radio waveband. It's not just TVs, it's not just mobile phones, but it could be television, it could be your microwave oven being too old and being closed improperly or operated improperly. It could be power lines, a bunch of other things, or it could be the thing that half the people on this planet love, and a very small fraction really hate. A bunch of extra satellites hanging around in the sky, burning up every so often, but also producing an excess amount of radio emission, which will blind our giant radio telescopes, super sensitive radio telescopes every so often. You can then get into the signal processing end of pulsar timing arrays, which you will almost never hear about. Which is you need these very high-speed conversion systems where the electromagnetic signals from the sky, which have been converted into electrical signals by the front end, by the horn, low noise amplifier, pipe down to the ground. You have some fancy processing, but you need to convert that electrical signal now into a representation which is easy to work with, which for modern pulsar systems is to store them for Stokes vectors. But of course, at the same time, you want to record the time with an extreme degree of precision at which every group of photons arrive. And the way you do that is you plug in this very expensive hydrogen laser, condition it with a GPS signal to improve its timing stability. And then for every fraction of the pulse that you observe from a pulsar, we divide these pulses down to phase bins of 1,000 or more, and then time type each phase bin very, very accurately at the picosecond. Well, if you're really lucky in the precise picoseconds, or if not a bit worse, but definitely much better than the hundreds of nanoseconds, which is our error on the residuals. And then you would store these this information somewhere on disk, which you would process. Well, maybe you wouldn't process, but a postdoc or a PhD student who's come along 10 years after you started working is going to sift through a lot of data, sift through a lot of data, and produce these beautiful pulsar timing data set, pulsar timing residuals, which you will, a group of other excited young people will take up as things to analyze and search for the strangest signals you can think of in the hopes of discovering this background. So that's one way of looking at how PTAs are built. Another more functional way of looking at how PTAs are built is to remember that it's a very, very iterative procedure. Because what we're always doing is we're observing these pulsars. We're trying to maximize the signal to noise of every observation, which is why we do this process called folding or stacking, which gives us a very, very bright pulse. We see almost no noise in this pulse. Compare that to a standard template using Fourier domain techniques. And you do that for a whole bunch of pulses observed over a whole bunch of different times. And then you try to measure the timing residuals, which, as I just mentioned, is what leads to the production of these very, very long PTA data sets. There's not much going on in this slide, except as a data analyst, as a PTA data analyst, I feel obliged to show you what a lot of us are spending our lives staring at. This is data not from the NPT, but from the European Pulsar Timing Area, which I work with a lot, where there are something of the order of 28 different observing systems, 6, 7 different telescopes. And what we are trying to do at this stage is to figure out if something is going wrong in lining up the POAs, lining up the timing at times of arrival from the different telescopes, from the different receivers, to produce a coherent solution. So whether or not my term is the timing solution is still valid. Sometimes we need to improve how things work. Sometimes we reach a point where we have so much data that all timing models will no longer be useful, which is where this iteration process kicks in. And you actually end up adding new parameters, you test for the value of these parameters, and then if it's significant enough, you can add new timing parameters, improving the precision of the timing model. Okay, that's all great and fantastic. What about how good is it? Typically, it's pretty good. We have less than 1% of outliers of our data sets. But what if everything went bonkers? I plugged in a whole bunch of bad data bats. Well, the good news is this doesn't kill my search for cryptographic background. This is a bit of a jump. I apologize, but because we'll come back to what the stochastic background is. But let's just pretend it's just a signal of interest to me at this point. I'm just trying to keep an eye on the time. But yeah, so the good news is, even if there is a fair amount of bad data in our data sets, because of the fact that in most PTAs we have tens of thousands of GeoArrays to fit our timing models to, it doesn't really throw us off, especially because we're not just using the data from one pulsar. What we are doing is we are searching for a correlated signal between many different pulsars. Again, this is something Sarah's already mentioned. I'm going backwards a little bit now, but I think in between all the rushing and some, I managed to move my slides around. Because the thing I did want to start with was dispersion measure, because that's in order. Because one of the biggest sources of unmodeled noise, or if you remember in the list of things that I put in, there were the timing parameters, which were the astrometric, the pulsar, and any other deterministic parameters, and then there was a bit about dispersion measure variations, the red noise properties, and pulsar jitter. So pulsar jitter is kind of hard to quantify unless you are doing very high precision measurements, but we are generally safe from jitter biasing our measurements completely. However, one of the bigger challenge is indeed to model the delays that density variations in the ionized gas between us and the pulsar is doing to us. So there are, again, there are many papers, and in fact, I don't even have space to put in some of the seminal papers on this topic. But dispersion measure variations, they arise from the fact that when you observe a pulsar across a wide band of frequency, you will see that high frequencies tend to arrive at a time which is much earlier than low frequencies for the same pulse. So this is actually not single pulse data, but this is average pulse. But for this pulsar, the delay is so large that it looks like the pulse is curved and gone over, and actually it falls back over and then comes in from here to finish off the. Now, this dispersion corresponds directly to the column density of electrons, which is passing through the line of sight between us and the pulsar. So if we can measure the dispersion delay, we can convert that back into a column density of sorts. This is a very unique measurement you can do mostly with pulsars alone. There is an automated technique, but the degree of precision is definitely quite different between pulsars and other techniques. In fact, if you have a low enough frequency of observation and a high enough frequency bandwidth, so the total amount of frequency channels you observe over, if they're large enough, and you're observing a low enough frequency, it's almost invisible on this plot. Based on my screen, I hope you can see better. But you can get down to a precision of 10 to 100 parts in a million, which is a fantastic thing to talk about when you are talking of measuring fluctuations in average density fluctuations over a path length of the order of 1 kiloparsec, which is kind of the average distance to most pulsars. So once you have this kind of fascinating precision, you can see all kinds of features popping up depending on where you are looking at in the sky. You can see long-term trends due to fluctuations in the interstellar medium, or you can see the sharp spikes, which actually correspond to an excess electron content contributed by the sun. Or you can pick up the sudden appearance or the sudden disappearance of of ionized material along the line of sight. So if there's a small underdensity of ionized gas passing through the line of sight, it will produce these very, very sharp dips in the timing variable. These are from a pulsar called PSR J1730 plus 0747. And these events are known as DM events. These remain some of the most difficult things to model in pulsar timing in general, as well as pulsar timing errors, because we inject very high frequency noise, which is difficult to remove and degrades performance quite a bit. So I mentioned very briefly here that some of these spikes, these annual spikes, are actually from an excess contribution from the sun. And the way this affects us is that this solar wind, which is a stream of ionized particles flowing out from the sun, is continuous but very dynamic and very variable. Unfortunately, it is also the closest source of ionized plasma to pulsar timers like you and me, which means anything that's going wrong or any changes in this thing is going to affect us very, very strongly. One thing you can do if you're interested is you can actually reverse the problem and say, if I can subtract off the usual ionospheric interstellar background, I can then go and investigate the properties of the solar wind passing through my line of sight. And if you're really, really lucky, you can even bump into a passing blob of plasma from the sun ejected in the form of a coronal mass ejection. Of course, we don't have to worry about this most of the time, but these are things which we are getting into more and more. Again, I'm not the only person writing these papers. A lot of work has been done on dispersion measure variations by Michael Lamb, by Jim Collins, and a lot of others. So I would encourage you to look at their work as well. We are getting to the position where not only the solar wind, but also the ionospheric turbulence can be a source of issues. At the frequencies we do usual pulsar timing array work, this is not a problem. But given the ever-increasing bandwidths of PTAs, this is going to become a problem sooner or later, where we will have to correct not only for non-terrestrial ionospheric issues, non-terrestrial ionized plasmas, we might also have to worry about ionospheric turbulence. This is incredibly hard and requires a lot of monitoring. And eventually, we will need to work with people who are looking very closely at the ionosphere itself using independent techniques. Okay, dispersion measure, yay, that was fun, not really, but it doesn't stop with the ionized part. If there's a cold and discrete structure hanging around in your line of sight, it is going to produce a whole bunch of effects. One of these things is to produce these beautiful, beautiful views of the pulsar in a certain sense, called scintillation patterns, which if you do a 2D Fourier transform can give you, if you're lucky, can produce these scintillation arcs, which are a direct measure of the size and the properties of this cold lump of matter hanging around in your line of sight. These can lead to some periodic signatures, but also the cold matter that has this annoying feature that it can produce a bunch of excess scattering delays, such as the one Rob Main has written about. Walter Briskin has mapped out using VLBI radio techniques as well, and Z-Wave looked at with very low frequency data and found that indeed it is quite a significant effect, producing delays of the order of an 0.1 to 0.2 microseconds. Sorry. I'm going to skip over this slide and move on to the next kind of noise, which is red noise. As I mentioned, one of the kinds of red noise we are interested in is the GWB, which means this is obviously something we want to be very careful about modeling out. We've already talked about the dispersion measure noise, which is what I mean by the turbulent ionized interstellar medium, which also happens to have a frequency-dependent characteristic. But there are a bunch of other features which are not dependent on the observing frequency. Those can be. Sorry, my slides. Okay, I have dropped a slide somewhere. So this is actually not a great example of a poorly modeled pulsar. It is, in fact, a very, very well modeled pulsar, which we have modeled for almost 40 years now. But you can see that it shows a huge amount of red noise power at the lower frequencies, which is where your gravitational wave signal lies. And if you want to use a pulsar like this in your PTA, you want to be able to model this red noise property very, very, very accurate. It's better if the red noise properties correspond only to the GWB, but more often than not, that's not the case. It is a competing noise source. So the way we go around this is actually going to be presented by Aurelio and Paul and others in a series in upcoming talks, where they will talk extensively about noise modeling in PTAs. But what we do try to do for PTA purposes is to fit these very long red noise processes, long-term red noise processes using power law models or some other approximate models to accurately model this. In recent work, Aurelio and a bunch of other people have shown that you can genuinely take the noise modeling at face value. It is working quite well. In fact, the deviation between the way we are doing modeling, which is to first fit a deterministic model and then search for non-deterministic components, and a full search where everything is fitted for jointly, is very, very low, except, of course, when some things are going off. And this is just a difference in the choice of coefficients that was used for this one. The PP plot, on the other hand, is the one we should be looking at, where through simulations, again, we can probe how well our noise models do. And this tells us that regardless of the recovered noise properties, based on the injection, we are almost always consistent with the injected noise properties, except for maybe DM, and this particular plot is limited by the fact that the simulation was mimicking narrowband data, which DM struggles with. The other thing that you want to build up is a lot of compute resources to do the kind of MCMC-based stochastic, MCMC-based analysis that we do. Well, it's not just MCMC, it can be any form of stochastic sampling, because unlike most other measurements that we talk about, we do not have a model which can be fitted in a frequent distance to a set of measurements and a p-value extracted. What we do instead is Bayesian analysis, and the way to do that is to resort to MCMCs, very high order MCMCs that take really, really long durations. But the good news is, independent of the method of stochastic sampling you choose, again, PTAs will generally work well. Okay, I think I'm getting towards the end of my allotted time, and I can now see all the slides that I had wished were before. But of course, what is the big interest in all of this? we are looking for gravitational waves, a whole bunch of gravitational waves overlapping on each other. Or if you're really lucky, maybe a really, really loud and nearby single source. And if we assume that the stochastic background is produced by binary black holes, supermassive binary black holes, then the region we are interested in is roughly towards the middle of this chart, because the PTA data sets are going to probe frequencies between a year, slightly less than a year, to tens of years, which gives you, so if you want to search for a signal, you want at least a couple of cycles of the sine wave like signal that you're searching for. And if the orbital periods of these distant supermassive black holes are tens of years, then you can search for the signals in your PTA data set. Okay, so what we've been able to do in the past is produce a whole bunch of these very, very stringent and ever decreasing upper limits. And this is a quick chart of all of those from the different PTAs. But one quick thing that I'd like you to take a look at is that so this little result, which is actually overlap, is from the PPTA, the IPTA data release 1, which uses data from here, and yet where every PTA produces a much higher upper limit, the combined data produces a much better limit. When I produced this plot, I didn't have the IPTA DR2, but the IPTA DR2 is about here. So it is a continuously decreasing trend in time, and every single time an IPTA data set has been produced, it has always performed better than the individual data sets. Okay, but the big impetus for a lot of work came through. Sorry, I hear some background noise.
Golam, if you can round up now, that would be great.
Okay, so I'll skip through these slides because you have probably seen a lot of these results somewhere else. But I will flash through the EPTA results, the individual PTA results. So as mentioned elsewhere, all PTAs are seeing between 3 and 4 sigma signal for a HD correlated signal in their individual PTA data sets. And of course, the next place to go would be the IPTA. So the good news is we have 115 pulsars from 5 different PTA data sets, which we are in the process of combining. And in fact, we have combined 20 of the longest, most sensitive pulsars already. We are starting work on the noise modeling aspects. And we hope to produce some results in the coming years. And in all of what I've said, it might be difficult to put across that a PTA or the IPTA is not built by a single person or a small group of people. So when I am speaking, I'm literally bringing to you the work of a few hundred people spread over 40 years. That's longer than I've been alive. So when I started making this talk, one of the things I wanted to really desperately try was to convey the sense of how much effort has been going on even before I came along and became a PhD student in pulsar astronomy, or started doing any PTA work for that matter. And this timeline, I hope, puts across all of those many, many results that lead us to where we are now, and all of the many, many steps that have brought us to where we are. The individual combinations from all of the PTAs, there is the emergence of the IPTA, and the emergence of the IPTA datasets, which I hope you were able to appreciate in the upper limits slide. And now we are at a place where we have evidence for HD correlations. The things to look forward to is a future full of gravitational wave astronomy at the nanohertz, and hopefully, even more excitingly, a world which is full of multi-messenger astronomy.
Okay, thank you very much, Golam. Do we have any quick questions? If I could ask one, is in terms of the pulsars which misbehave, do we have any physical insights into the course of that? Is there some correlation with a property of the pulsar?
So yes, but it is really a pulsar by pulsar thing, because for some pulsars, it is the fact that they are too close. So there is this, the brightest millisecond pulsar, J0437, is very bright, but it's very, very close, which leads to, well, not very, very close, not these are very close, but it's close enough that the amount of ionized gas between us changes quite dramatically between observations. And it is bright enough that it's also able to map a lot of the structures along the line of sight. So these lead to a whole host of effects and can produce red noise. Then there is the first millisecond pulsar, J1939, where there are intrinsic processes in the pulsar, which we are not quite sure of. Then there are occasionally pulsars like J0613, which before we started gathering our PTA dataset had a glitch, and then spent a long time recovering from that glitch. And because initially we didn't know there was a glitch, this was all modeled as red noise. And then some very clever PhD student managed to find some archival data and show that, in fact, there was a glitch in this pulsar. So it's different for different pulsars, but very often, more often than not, we can pin down the physical processes.
Cool. Okay, thank you. Doesn't look like we have any other questions currently. So I hope everyone will thank Golam for the introduction to the IPTA. And we'll take a 5-minute break before the final talk of this session from Flor. Okay, thank you, everyone. Hello, everyone. Welcome back. We're about to get started with the third and final talk of our session on pulsing time array discoveries and gravitational wave astrophysics. And we'll be rounding off the session now. I anticipate looking at some of the smaller black holes with a talk from Dr. Flor Broekgaarden, who is newly a PhD student from the Center for Astrophysics in Harvard, and is now moving to new positions in New York with Columbia and the Flatiron Institute. So let's get started. Flor, please tell us about gravitational wave paleontology and the new discoveries that come from that.
Yeah, thank you so much. I think everyone can hear me. Yeah. So today I'm going to shift gears a little bit and talk about the gravitational waves from black holes that come from stellar mass stars, basically, or stellar mass black holes that come from stars. And specifically, I'd like to basically advertise that I think these black holes are awesome because they actually tell us about the dinosaurs of our universe, which are the massive stars that form them. And I'll tell you a bit why, and why then this field becomes like gravitational wave paleontology. But to start, compared to our sun that's shown here in yellow, massive stars that I'll be talking about are these stars that are 10 to 200 times the size of our own sun. They're extremely rare. The IMF, that initial mass function, tells us that only 1 in every 1,000 stars is typically formed as such a massive star. And they also live fast and die young, with lifetimes that are typically 1,000 times smaller than that of our own sun. And this is why these stars are so rare, and it's so challenging to observe a statistical significant populations of these massive stars and understand their physics and learn from them. And so right now, to study these massive stars, we often rely in our own Milky Way on very, very expensive surveys going star by star that are very, very challenging. And it becomes basically impossible to study and observe these massive stars in galaxies like much further away from us, in like distant galaxies as you see here. And so because of this reason, very little is known about these massive stars. It's just so hard to observe them. But there's one thing we do know, and this is that they play a pivotal role in shaping our universe through all these different processes shown here. So for instance, they trace and trigger star formation. Their strong stellar winds provide a lot of feedback into our universe and galaxies. They produce these transients, such as X-ray binaries or supernovae. They often outshine star-forming galaxies, especially early on in our universe. They might be the reason for the reionization early on in the universe, and they produce black holes and neutron stars when they die. And if that's not enough, they also are responsible for many heavy element productions, such as like all the oxygen that we breathe today here on Earth. Another super cool thing about these massive stars is that they often live in pairs, in a binary, or even multiple, like a triple system. And these stars, when they're in a pair, it drastically alters their life. They can exchange mass during their involution, so one star can eat a little bit of the mass of the other. And these massive stars, when they go supernova, or when they die, they go supernova and form a black hole. Now, I didn't have the budget of Interstellar to really visualize those black holes. So from here on, I'm just going to show them with marbles shown here. And so these massive stars, if they're in a pair and they can survive all these explosive phases, and one can go a black hole and the other can form a black hole, you might end up with a pair of two black holes shown here with these two marbles. And these black holes might spiral in over many, many billions of years and eventually collide, producing a slightly more massive black hole, as you probably all know. Now, so the exciting thing is that as of 2015, we can now observe these black hole collisions through gravitational waves. And so this is the reason that people like me started asking the important question and looking at the opportunity, whether we can use these black hole collisions as fossils to study how their massive stars once formed, lived, and died in the distant past. And so this is what I and others refer to when we usually say gravitational wave paleontology. So similar how people study fossils, we want to study the massive stars, or use fossils to study dinosaurs. We want to use like the fossils of massive stars, black holes, to study how these stars once formed, lived, and died. Okay, so just a quick recap is how do we detect these systems? Well, all around our universe, there are these black holes that collide, as we now know. And when they collide, they produce these gravitational waves that can travel through millions of years through space and eventually reach us here on Earth, where they produce these wiggles in Earth itself, in space-time itself, that we can then detect on Earth. Now, this one is a bit exaggerated, but we have these ground-based LIGO and Virgo and Kaga like interferometers that can detect these signals as the wave passes through. Now, importantly, these signals, called chirps, from these signals, we can infer the properties of the black holes, such as their masses, mass ratios, and even properties like their spins. And so we want to use that to learn about massive stars. Now, there's one thing that's really, really cool about these black hole observations that makes them really, really perfect to do gravitational wave paleontology. And this is that they actually probe the entire universe. Now, to show that, here's like a picture of the universe where early on, we have the Big Bang at the start of the universe, and then the first stars and galaxy formation. And then as you move to the right, we end up in the present day, where the Earth is. Now, the cool thing is that these stars maybe form their pairs of black holes in just a few million years, it can actually take up to many billions of years before the black holes eventually collide. So this is a very, very long process. This is just an animation. In real time, the black holes don't move through space like this, but they reside in a galaxy that like evolves over time until the present day redshift. But what this means is that the black hole collisions that we see today already probe massive stars and how they formed, lived, and died much, much earlier in our universe to much higher redshifts. However, there's also something else that's very important from this, which is that if we want to learn about the stars, these black hole collisions actually don't directly tell us the properties of the stars. So instead, what we need to do is we need to like forward model how these stars form, live, and die to see what imprints they leave behind on the black hole collisions. Compare it how maybe paleontologists cannot directly tell from a fossil whether a dinosaur had feathers, but they can manage, like they can model like dinosaurs with feathers and see what imprints they leave behind. So we have to do the same in this case and really forward model these stars and see what imprints they leave behind to test our theories. Now, in practice, it looks something like this as an animation. So we have these stellar evolution models that take in hypothetical pairs of stars. So stars with, for instance, different masses, different properties, mass ratios. And then this model takes into account everything like the stellar evolution, stellar winds, physical properties, and processes during the evolution, and determines whether your hypothetical pair of stars can form, in this case, a black hole merger, here shown with like a black marble coming out. And so this is great, right? So going back to this picture, we have these observations. We want to learn about the stars, and we now have these stellar evolution models. Now, if there's one thing I hope you remember from this talk, is that this part of this diagram, so figuring out how these stars evolve and comparing that with observations, is actually not that easy. And I'll basically going to discuss for the remaining of the talk that there's 5 key challenges, like key barriers that we have to overcome before we can properly model and understand how these stars evolve and what gravitational wave sources they form. And I call this the so-called gravitational wave paleontology uncertainty challenge, because there's basically 5 uncertainties or challenges that we need to overcome to do this. Okay, so let's walk you through it. So first of all, the first challenge or barrier we have to overcome is that we actually are not sure how these gravitational wave sources form. There's different formation channels or formation pathways or theories that people have come up with that might explain how you get 2 black holes, how you form 2 black holes that can then collide in our universe and observe. So to give you an example, here in the top left is called isolated binary evolution. And in this scenario, you start with a wide pair of massive stars. These stars then evolve, and so the first star, the more massive star, evolves fastest, and eventually expands to a giant star, in which case it can like transfer mass into the companion star. This eventually stops when you're left with like a helium or a stripped star with a companion star. Now this star might go supernova and eventually leave behind the first compact object, here a black hole. But in most cases, actually, the supernova disrupts the system. But we're going to look at systems that continue to survive. Okay, then the second star might also evolve. There might be an X-ray binary phase. But eventually, when it expands, it also fills its rush low and can transfer mass onto the black hole. But in this case, this mass transfer is dynamically unstable. And so what happens is that there might be what we call a common envelope phase, where basically the compact object is engulfed in the envelope of the other star, and due to drag, slowly rotates in, spirals in, until it becomes really, really close to the core of the other star. And if this star can successfully eject the envelope due to heating, you might actually end up with a very, very tight binary, shown here, consisting of the black hole and then this helium star. But the important thing is that they're now much, much more closer as a binary. Now, this second star might also go supernova and form the second compact object, either a neutron star or a black hole. And if this compact object system here is close enough, they can actually spiral in within the age of the universe and collide, producing one of the gravitational wave sources that we might see and observe today. However, as you maybe also saw, this is just one of many formation channels. In practice, we have many, many ideas and theories of how these systems might form. So to give a few examples, they might actually form from population 3 stars, which are these very early in the universe, the first generation of stars that are very low metallicities and can stay small and thereby get closer together. They might form chemically homogeneous. There's a talk later on Thursday and Friday about this, where you start with 2 very low metallicity massive stars so close to each other that they actually start mixing their material and also can stay small. And they might actually form from higher order multiples or triples, like a triple system or quadruple system. On the other hand, there's also this kind of second category of channels where instead of being isolated, like the few stars are together, they're now in these dense stellar environments, such as globular clusters, young or open star clusters, or a nuclear star cluster, say a disk around a supermassive black hole. Where now there's so many stars that they can undergo all these like 3-body interactions or interaction with their environments, and also produce black hole binaries that collide, where especially these 3-body interactions might actually help them in getting closer together. On the other hand, there's many, many more formation channels proposed, and you can even like summarize here, including that they might actually form from primordial black holes or cosmic strings, as well as from flybys of stars. Okay, so in practice, what we have to do to properly model all these stars and do this forward modeling and compare with observations is that we basically have to rerun or run our simulations, but for all these different formation channels. And so this becomes already very, very computationally expensive since you need to include many different physics, but really need to run many, many different environments. Okay, so that's the first challenge in doing this. Now, the second challenge is that the initial conditions of how these stars form and how many stars form are actually very, very uncertain. So things like how many stars are in a binary to begin with, or in a triple? What are the initial properties, such as the initial masses, initial mass ratios, initial rotation, and especially what is the initial metallicity of stars throughout the universe? And so this turns out to be a very, very important property, since we now know that birth metallicities of stars, so with what metallicity stars form, can drastically impact and alter what the binary black hole merger might look like. So for instance, this is a paper or a figure from Giacobo and Mappelli, where it shows as a function of metallicity, here in different colors, for the stars to begin with, what the total masses of the black hole collisions are. And so you see, as you basically go from low metallicity to higher metallicity, that the total mass of the black hole collision drastically changes as a function of the birth metallicity of stars. And we see this in many codes. And so in practice, we should not just only model these 2 axes of different masses for the hypothetical stars, but we actually have to like model and try to understand how all these different initial conditions that the stars can have impact the star's evolution. And so we have to really run our simulations, our stellar evolution simulations, for many, many of these different initial conditions to test how they impact the outcome. Now, the third one, and maybe my favorite one, is that these gravitational wave sources are actually an extremely rare outcome among stars, both in real life, in our universe, as well as in those simulations. So to give an example, if I simulate 1,000 massive star binaries, even already focusing around the stars that I'm interested in, typically only one of those 1,000 binaries actually becomes a gravitational wave source. So in most cases, when you start with 2 massive stars, they disrupt during the supernova or otherwise merge as stars, but not as gravitational wave sources. So it's kind of like relationships maybe on Earth, where most of them break up, but we're looking for that like 1 in 1,000 that stays together, and we want to know why. And this is important because actually it means that we need to get a big enough sample of gravitational wave sources in our simulations. We need to really, really run even more, like 1,000 times more stars to begin with. And this is important because otherwise you get these like Poisson uncertainties in our distributions when we compare like simulation outcomes with observations that we want to get rid of. So yeah, in practice, we have to basically run our simulations even longer, like 1,000 times longer than your typical simulations maybe, just to make sure we find enough of these data points to begin with, so we can make a fair comparison. Now we get into maybe the two biggest challenges, where the first one is that the stellar evolution is actually very, very uncertain. So I showed you this evolutionary path of one of the formation channels before. But one thing that's important to realize is that there's all these different phases, mass transfer, supernova, and much of the underlying physics of these stellar evolution phases is highly uncertain. And so in practice, what we need to do is to model this uncertainty. And so this often comes down to basically putting knobs for these different phases. So we use parameterized prescriptions for mass transfer evolution, for supernova, where we model the uncertainty using like knobs that we can vary, or we can like vary some of the physics values. And then we rerun our entire simulations to test how this impacts our results. So again, there's this fourth barrier where we have to rerun our entire set of simulations with already all these other extra costs to just test how different physics assumptions like impact our results. Now, the fifth and maybe biggest barrier is that actually stellar evolution is really, really, really uncertain. So to give an example, to model a supernova, often in our simulation, it looks something like this. It's just kind of a set of equation and parameterized prescriptions where we have to have some free parameters like the B2, like B sub 2 here. And then based on masses of stars that our code keeps track of, we assign it some like final mass, like say black hole mass. However, of course, in practice, if we look at more detailed simulations, we actually find that things look maybe more like this, like way more messy, there's more physics involved. It's not as easy as just writing down 4 equations and being done to describe all the complex physics that's going on in many of these stellar evolutionary phases. And so what we really, really have to do is basically implement more expensive and hopefully more detailed or better physics models into our simulations to do a better job at like understanding these uncertainties from the modeling, but also understanding the physics that's important for stellar evolution and for forming these gravitational wave sources. Okay, so we have these 5 challenges. And so although it's super, super awesome that we want to like model these stars, how they evolve and what gravitational wave sources they make. And since it can become so important to do that, to learn about stars and to do gravitational wave paleontology, I would say maybe a fair representation of what our field sometimes feels like today is something like this. Where basically, as like a gravitational wave paleontologist, you're trying to like overcome these hurdles, but there's just more and more hurdles that we are falling over in order to model these sources. And I wanted to give you an example of how this, what this looks like in our actual simulations. So in the next video, I'll show you here on the x-axis, it's going to show you the local black hole merger rate density. So this is the number of black holes in our local universe, so nearby us at redshift 0, that are colliding with each other per volume, so per gigaparsec cube volume, per time, so per year. And so what you'll see is it's going to flip through a lot of these simulations, like stellar evolution simulation efforts. What you see now is first the gravitational wave observations. So LIGO, Virgo, Kagra have observed about 100 black hole collisions to date, and they know what like volume they're sensitive to. So from this, they can derive like how many black hole collisions there are locally in a universe per year per volume. Now, LIGO found something for binary black holes between 10 and 100 black hole collisions per gigaparsec cube per year. They have 4 different estimates like shown here with the median shown as a dot and then like a line showing the interval. And these 4 different estimates are based on slightly different assumptions that they assume for the underlying mass distribution of those sources that like slightly impacts their expectations. But overall, you can see it lies somewhere between 10 and 100. Now, how do our simulations do? As I now play this video, it's actually going to show you and flip through more than 200 of those studies of stellar evolution simulations. And each color here represents with a different formation channel that I showed you in an earlier slide. So for instance, these are these population 3 stars, and now it's like black holes that form from globular clusters. Now, in each panel, scatter points, like each horizontal line is one study, like one paper or one PhD student or postdoc or professor that did all this work, did their stellar evolution simulations, and then calculated, for instance, how often these black holes collide from their hypothetical like population synthesis simulation. Now, scatter points basically mean different simulations. So in one study, they would run their simulation, then maybe change some of the physics, and those are the different scatter points. So it's different simulation outcomes from the same underlying model, but with slightly different assumptions. And then what we did is we connected them with a line to show you the range. And so now it's flipping actually already to the neutron star black holes. But basically what you see, for instance, now we look at binary neutron stars, that we have some rates from gravitational waves. We actually have some rates from electromagnetic observations, such as pulsars, which are quite aligned and kind of the same order of magnitude. But then once we go to simulations, we have these huge ranges of expected range that span easily like 4 or 5 orders of magnitude across this plot. And so this is really an impact from uncertainties. So just different uncertainties and assumptions that you make in your models give drastically different outcomes in your simulations. And so that's important because on one hand, it means that it's very, very complicated to actually do this picture, but also might mean that maybe eventually we might be able to learn about the underlying physics by constraining these kind of rates. It becomes worse. So one thing we can also ask is, this was just a local rates, but what about different formation histories, or basically different physical processes that these stars go through before they form a gravitational wave source? So in this case, for instance, if you just focus on this isolated binary evolution channel, then typically we think it's classified by first having a stable mass transfer phase and then having a common envelope phase. But more recently, in the past years, people have also suggested that maybe sometimes you form these systems without a common envelope phase. So in both cases, it's a stable mass transfer phase. And so one thing you might wonder is, like, say you take all the models for isolated binary evolution that kind of give the same rate, the same order of magnitude rates for how often black holes collide. Do these codes agree for how these systems actually formed from pairs of massive stars? And so in this case, the question is, for instance, do we agree on whether they have to go through a common envelope phase or instead don't go through a common envelope phase? And so I compared all these different population stellar evolution models. And what I find is this. So here it shows in orange, basically it says there's no common envelope phase that they experience. In blue, it says it does experience a common envelope phase. And then here on the x-axis, it shows you the fraction of black hole collisions that LIGO sees today that had to go through one of these phases. And so what you see is that different codes drastically have different answers to this question. So you might be here in the top in this simulation where basically none of them form through a common envelope phase. Whereas if you're in the bottom here, actually with the same rate, it actually argues that they all must come from and have experienced a common envelope phase. And so this is important because, you know, if you want to learn about common envelope phases and these stellar evolution from gravitational waves, it becomes really important to start constraining how much we can truly learn from these gravitational wave sources about these phases. And so hopefully in the future, we can like narrow down in which region we are, so we can say whether, for instance, black holes probe common envelope phases. Okay, with all this said, you might wonder by now, maybe you're already pessimistic and left the chat. I hope not. But you might wonder by now, with all these uncertainties, is there any hope to do gravitational wave paleontology? And I would argue for the rest of this talk that yes, we can do gravitational wave paleontology. It will be super, super exciting. But the most important thing is we cannot do it alone or like as a single person. We really need you. And especially as I will demonstrate in the remaining of my talk, I think we really require kind of a lot of different avenues to constrain better physics, lower these barriers, understand these barriers, and overcome some of these challenges. And I'm now gonna like show you a couple of examples of what people are working on. People are working on tons of things, but I'm gonna show you mostly a couple of things from the past year, like the most kind of recent, some of the most recent works that people have been doing. Okay, so what's been going on? So for instance, this year, Milano-Bicocca published this really cool paper where he's trying to model, similar to some other people, for the first time also different formation pathways at the same time, basically through the same code, so we can do a fair comparison. And I think this is very, very exciting work, this and many others, because as you can see, you can kind of do a direct comparison for which formation channels using the same kind of initial conditions, what distributions they make in, for instance, binary black hole masses. So you see here that like the isolated and dynamical channels have different expectations for how massive their black holes can be. And so one very, very interesting avenue, and there's lots of talk on Thursday and Friday, so I'm not going to mention it in much detail, is that people are starting looking at, instead of just rates, at how different formation channels give different predictions for instance, redshift evolution rates, but also the properties of these black holes, such as their masses over time. And so I think this kind of work is really, really exciting, and will help us a lot in like understanding how we can discriminate between channels. At the same time, actually from observations, and there's also lots of talks, excitingly, the rest of the week about this, but also from observations, people are trying to understand this. And so there's a lot of efforts in the past year. So for instance, by Godfrey et al., 2023, where they're trying to understand from observations if they can infer and distinguish different populations, such as here, where they find kind of like a population that it has this like peak around 10 solar masses, and then like a broader population, which they think might hint towards different formation pathways that you can distinguish from observations. Now, the second challenge of understanding initial conditions. Well, there's a lot of effort on the way and in progress of better understanding initial conditions and how these initial conditions impact our stellar evolution expectations for binary black holes, black hole neutron stars, and binary neutron star mergers. So I wanted to highlight this work by Srinivasan et al. 2023, where they actually started to like look at the galaxy properties and how that impacts, or different galaxies impact where these binary black holes are formed. And one interesting plot that they show is that, for instance, if they plot as a function of metallicity, how many stars form, for instance, a black hole pair that can collide and form a gravitational wave source, they find that although most stars maybe form from higher metallicity, so most stars are formed here, that actually the black hole formation is much more efficient at low metallicities. So even though maybe fewer stars form from lower metallicity, they might actually outplay and play a really, really big role in forming the black holes collisions, just because they're so much better at forming black holes than higher metallicity stars. And this mostly has to do with that metallicity, or stellar winds are metallicity dependent. So at lower metallicity, there's much less stellar winds that are often iron and metallicity driven. And so these stars lose fewer mass, they can kind of stay bigger, and that helps you in forming a pair of black holes. And similar work has been like confirmed and has been earlier found, but this, for instance, in this work, they put it into perspective of galaxy types. And there's more interesting work, such as by Uriel, 2023, where they find like similar results, even when they vary a lot of their stellar evolution assumptions in all these different models. So here you always see this kind of like rapid decline, which basically means that at lower metallicity, you're much, much more efficient. And this is good news for us because it means that there's maybe some robust findings, like maybe we can say robustly that this trend is there, that as you go to higher metallicity, you become very inefficient in forming black hole mergers, which will then help us understand where do these black holes come from and like where do they form, like what environments should we see them form in. So I think this is very exciting results. And for instance, other authors such as Chris Linke et al. 2023, and there was also work by Brill et al. Recently, put this also into context of implementing then how stars form as a function of time and with what metallicities they work, and for different functions and assumptions in that, understanding how it impacts the, for instance, expected merger rates of these distributions, which I think is super, super interesting. Now, in addition, there was also really cool recent work by Santoro-Guido et al. In 2023, where they also started doing and modeling these uncertainties of initial conditions. So how many stars form, with what metallicity do they exactly form, but then for other formation channels, such as population 3 stars, which I think is really, really cool, where we're starting to understand how these different uncertainties impact our expectations. And also, thanks to work to, for instance, speed up codes such as to model global clusters, we also can, and this is work by like so-called code raster, we can start to like truly model and like understand also how uncertainties impact, for instance, the merger rate coming from these other formation channels. And there's much work on this as well, trying to understand how not knowing how global clusters form and when they exactly form and their star formation rate at least impacts our expectations to understand the constraints, like what are the uncertainties, what do we know, and how can we constrain them, which I think is very cool work. Now, more work to speed up our simulations is being done by Rocha et al. 2022, I think was a very, very exciting paper, where they basically developed this new machine learning algorithm, Cycrise, to basically use fewer simulation points, shown here with black dots, to get the same outcome or like same stellar evolution computation, here shown with these different colors, as with the larger grid. And so there's a lot of people working on these machine learning and AI methods to basically speed up our simulation. And I know Case Wang has a talk later this week as well that I think will go more into depth about this like exciting prospects of speeding up our simulations and like why this is so important for us to do. At the same time, we're also improving the stellar evolution. And so one example is, for instance, that many of the past codes have always used the same stellar evolution tracks. So even the same tracks for how does a star evolve, just a single star, how does it like evolve, change its life, etc. And so in most codes actually use a prescription that looks something like this. So it's from 2000 and 2002. And it is actually very sparse grids that's incomplete for stars above 50 solar masses and has like many gaps and it's just not up to date with current knowledge. And so I'm very, very excited that there's actually many work on the way to improve this and, for instance, implement more computationally expensive, but also more detailed and hopefully what we think more accurate stellar tracks that are way more detailed in the evolution and have like updated stellar physics in how these stars evolve from like a main sequence star to black holes and compact objects, which I think is very, very exciting. And so this is important as, for instance, Agrawal et al. Showed in 2023, because like which track you use here shown with these different, in these different squares really impacts what stellar evolution phases they go through. And that's here, different colors basically show different stellar evolution phases. For the experts, it's different mass transfer cases. Yeah, thanks, Chris. Okay, in addition, the thing that I'm very excited about is also that there's much more other observation that we can use to constrain some of the stellar physics. So again, I showed you this picture, but one of the exciting parts is that there's like these different phases where there's like helium stars with a companion. And now, since the past year and 2 years, we can observe these. So, for example, a few of this kind of systems in this phase have now been found as either black hole imposters or Gaia black holes. Then we'll hopefully see more of these kind of intermediate stage systems, hopefully also the ones that are closer to the ones that we think might form gravitational wave sources. And most excitingly, these helium stars, we hadn't found them in a long time. But as of last week, Maria Draut and Ilva Goldberg published a paper where they actually found this missing population of helium stars, here shown in blue circles, that I think will really help us understand further, like how these stars evolve, what their masses are, and for instance, what their wind loss is, which are one of the biggest uncertainties in our models. And similar constraints can be found from like other observations, like many electromagnetic observations, such as, for instance, supernova. So these supernova that we're catching really early, I think, tell an interesting story about the mass loss of these stars at the end of their lives that becomes really important to understand the pre-supernova conditions, but also the supernova conditions of these massive stars. Yeah, and basically as the last part, there's also a lot of work on the way. This was very recently published of like understanding how these gravitational wave mergers, like understanding them also in the perspective of, for instance, putting them in galaxy surveys, such as work from Ralph et al. And Heloise Stevens, who, for instance, used the properties of 170817 host galaxy to better understand what the progenitors of this system might be. And so I think these are very interesting prospects to better understand our sources. Okay, and so to end with, I wanted to go back to this, or basically want to show this picture where these developments in this field of gravitational wave paleontology basically couldn't come at a better time, because it's very exciting that currently, you know, we started with a few observations in 2015, but this is rapidly going to explode in the coming decades. And so this shows you a timeline of the simulations where we maybe started with a few, you know, first 100 detections, but in 04 are expecting to double it, 05 expecting to double it, and then with these future telescopes, the expectation is actually that we're going to detect hundreds of thousands of these gravitational wave sources per year, which will just completely dwarf the few systems, or like the 100 systems that we've seen today, which I think is very exciting. And so I would argue that these future detectors, like the Cosmic Explorer and Einstein Telescope, could actually provide a unique instrument to basically study massive stars for $100 a star, which is what you come down to if you kind of calculate that a Cosmic Explorer costs like a few $1 billion. But this is only true if we can truly connect these gravitational wave sources to their progenitor stars by doing gravitational wave paleontology. And so this is challenging, but it's very exciting and has a lot of really exciting prospects. And especially, maybe one thing that's really important to know is that not only will we just see more gravitational wave sources, we're actually going to detect it much further out. So currently, we kind of see black hole mergers up to redshift 1 with LIGO. But these future detectors, like next generation detectors, they're going to increase where we see, to what distance we see black hole mergers beyond like redshift 10, and possibly even like beyond redshift 20 and 30. And so practically, it means that we might see every single merging black hole, stellar mass black hole in the universe, which is just super exciting, and will give us a lot of information about how these systems change as a function of redshift, which will also help us understand these formation channels. And of course, very importantly, as the early talks has shown, we're also going to get all these other information from all these different surveys that maybe probe like other types of sources. But for instance, LISA is also going to probe double white dwarfs and might see some neutron star and black hole binaries that can further inform us about the physics of these things. And of course, we're going to have a ton of electromagnetic surveys, GWST, like cool telescopes that will hopefully also help us better understand a lot of these processes underlying gravitational wave paleontology. Okay, so to end, I hope that this gives some optimism that maybe today we're in this left picture where when we're doing gravitational wave paleontology, we're experiencing all these different barriers that we have to overcome. But in the coming 10, 20 years, like with all the hard work we're already doing, and even more hard work by both our community and especially many of you who are listening today, I really hope we can go to this like right picture where we're starting to understand and constrain some of these barriers and understand how we can overcome them to properly model stars and open up the new frontier of gravitational wave paleontology. And this is important as that will allow us to truly use these gravitational wave mergers to understand how these massive stars once formed, lived, and died. And that in turn is like so important, as these massive stars, again, are responsible for so many of the physical processes in our universe that we will hopefully be able to better understand using gravitational waves and gravitational wave paleontology. So on that note, I say thank you, and I'll open it up for questions.
Thank you, Flo. For everyone, the Q&A is open. Please type your questions there. While you're pondering and typing, I'd like to take the opportunity as chair to ask a question, which is, well, I was hoping, Flo, you could maybe pick one of the non-gravitational wave channels you mentioned, which you think would be the most useful for helping uncover the extra physics we know. So there's one electromagnetic observable you'd really want. What would you go for?
Yeah, that's a great question. So I would say those helium stars, like observing tons of helium stars, will be very, very helpful to basically understand how these strip stars live and evolve, and I think we're pretty certain that, at least if they come from these binary stars, that almost all gravitational sources have like strip stars somewhere in their lives. So understanding like their properties, like how they live, how they lose mass, how they evolve, how they expand, I think is a crucial part of kind of seeing like an intermediate phase of those gravitational wave sources. So I would place my bet on something like this.
Oh, thank you. We're still not got any questions. It might be that everyone is a bit tired after the end of all the books. Okay. While we're on this topic, though, of the strip slides, I'll take a moment more. Is there a particular instrument that you would really like for the future for finding more strip?
Yeah, I would say especially UV, like space UV instruments, because often, as you can also see here, and I have like a separate plot, but often to identify these stars, you need really good like UV telescopes that can identify some of the elements from spectral lines that only show up in the UV. And so UV instruments go to space so they can observe and try to see and find those stars, not just nearby. So these are from the LMC and SMC, but in further distance galaxies. So you'd kind of have to go to a next generation James Webb Telescope. There's one that was at least advertised by the Decadal Survey a few years ago, which is it's now called the Habitable Worlds. But it's basically like a LUVOIR and HabX combined into one big expensive telescope in the UV and other spectra that would be able to do this.
Cool. Okay, yes, we definitely want UV, and that is hard to get from the ground. Okay,
yes.
We have a comment rather than a question in the chat saying beautiful talk. So good work there. We have a question from Jocelyn Reed, who's wondering about how well we can predict the next generation populations and how big is the impact of cosmology. I think possibly there it's metallicity, star formation rate and things like that.
Yeah, that's a great question. Thank you, Justin. So I think it's hard. At the moment, it's hard. So there are several studies. There's like Iacovelli is going to give a talk, I think, on Thursday and Friday that has some expectations for the number of mergers that we might see with next generation telescopes. But I think the true answer is that this is still highly uncertain. Like, for instance, imagine that somehow our universe doesn't produce any black holes beyond redshift 1, right? Or 1.5 that we've seen today. Like, then all of a sudden, you wouldn't see any black hole mergers, even though our expectations are they are there. So it would drastically impact the results. Now, I think most people agree that that's very, very unlikely. But these uncertainties are certainly there, and there's certainly stellar evolution processes that we just don't understand that can still drastically like alter how many of them should be formed in the universe. And I think you're right. So in the past years, I think one thing we have learned in like the past, especially past 3 years from many studies, is that especially what metallicity stars form over cosmic time is really, really important for how many, for instance, black hole collisions form. And we don't understand that well because it's really difficult and challenging to understand and observe the metallicities of stars, star formation at galaxies at any redshift, but especially beyond redshift 2. So I think, yeah, what will really help is to better further understand how those different uncertainties impact our results. So we have to do more theoretical predictions, but then also on the observational aspect, it's really having more observations of galaxies, especially higher up, and understanding the star formation metallicity would be really, really helpful. But I've seen some studies where it took many tech nights and you still get a huge error bar on star forming uncertainty. So yeah, I'm hopeful, but I think there's a lot of challenges there.
Cool. Okay, excellent. We have a big question here, potentially, I think, from Lisa Drummond, asking, can you comment on the potential for machine learning to help you overcome the challenges you mentioned?
Yeah, I think machine learning is going to be huge in doing this. And so I know Kees Wang is giving a talk later this week on this too. But I think there's two aspects. So the first one is so it's mostly to speed up our simulations. So to make some of the things that are now really hard, and very computationally expensive, less expensive. So things like the interpolation, things like how if we have a model for supernova, like those hydro models, can we somehow find a way to make that less expensive and plug it into our simulations? And then two big other areas are first comparing it with observations. There's a huge statistical analysis there for how do you compare these models properly with observations in a statistically robust way. So there's a lot of machine learning there in kind of the data comparison, Bayesian analysis, as well as how do we just find more of these rare events in our simulation? So there you come into sampling methods and that can really help us speed up these simulations. So I think there's a ton of AI and machine learning prospects. Happy to talk more offline to point you to some papers and brainstorm about this. Yeah.
Okay, we have another question from Tom Dent asking potentially the reverse of my question. What type of info would be useful to have from gravitational wave collaborations in addition to what we already release?
No, great. So I think what would be really, really helpful is to basically have correlated distributions. So LIGO is already in the latest population paper from GWDC3. It already released, for instance, the rate as a function of redshift, which I think is super, super helpful. But I would also like to, for instance, see how the mass evolves as a function of redshift, or mass ratios evolve as a function of redshift, or even all of them at the same time. I think that will be very insightful and really start to provide us with handles of okay, there's in one-dimensional plots are kind of easy. You can tweak some knobs and you can still make the same one-dimensional plot. But once you go to correlated functions, it's much, much more challenging to basically change one knob and still get the same output. So I think that's really going to be key. Mass as function of redshift evolution of basically almost everything, say mass ratio or spins, I think would be very useful.
Okay, great.
Or blessing. Yes, I'm blessing. Having some, another 10 binary neutron star mergers with EM counterpart would be great, but and a black hole neutron star one, but I think that's asking for too much.
we can see what we can do, but no guarantees. I'm seeing we also have a hand up from Scott, who I guess as a host can't ask a question.
Yeah, that's right. I can't use the Q&A, so I'll just ask it this way. Really nice talk, Flora. So and it's related to the machine learning question that you had. So I was just wondering what your opinion is on the future of the uncertainties of modeling the stellar evolution and binary evolution. How much do you think the current problems and the uncertainties in those two topics are due to we just don't have the full amount of physics in there, i.e. we need much more detailed individual dots on these, or do we just need to really sample this whole range where I think, like you were saying, machine learning will really help with the interpolation, or is it a combination of both?
That's a great question. And unfortunately, I think it's a combination. So, because I think one of the important things is like, yes, we need more detailed stellar evolution prescriptions. There's no doubt that the way we are modeling common envelope physics or mass transfer physics or supernova is like not as detailed enough to like fully understand it. But then in order to do that, I think the first question is almost like, how important are, like, what should we focus on in the coming 10, 20 years, right? Like, where should we put our computational time? Where should we put our people, our human time? And so in order to do that, you still first have to go back and do your simulations and figure out how do, for instance, like changing these prescriptions for more detailed prescriptions, like change the outcome, right? If it doesn't change the outcome at all, in some ways we're maybe happy because maybe that process, like that evolutionary stage wasn't so important, right? It could be that none of them formed through a common envelope phase. So maybe we don't have to spend our time on putting in more detailed common envelope prescriptions. But in order to get there, then you really need these like a large enough statistical sample that explores enough of the current known uncertainties to fully say, okay, no matter, if we twiggled all these knobs, we still didn't find that any of them formed through a common envelope. So we can, leave the common envelope off the table. We don't have to focus our time there. But so to do that, you really have to go to like these machine learning algorithms that can help you explore this like high dimensional parameter space that just currently no one is fully exploring. Like we're not there yet just because of the computational limits. So I think that's almost a very, very important first step before we can test like even like know which of the detailed physics are we missing or should we really focus on.
Great, thank you.
Okay, I think we have exhausted our question and answers for now. Thank you, Floor, so much for the talk and the discussion, and thank you everyone for asking the questions. Thank you to Sarah and Golam for their talks earlier in the session. We will conclude for now and hopefully see you for various more exciting talks throughout the Amaldi program.
Yeah, thanks, Christopher. Thanks, everyone.
Yeah, thanks, everyone. The next session will be at 2200 UTC. See you all then, hopefully.
Thank you.